You know, for years getting root on a kernel followed a pretty simple recipe. Find a bug, overwrite a function pointer, and bam, you're in. Well, that era is officially over. Modern defenses have slammed that door shut. So what happens when the old ways die? Something new, way more elegant, and honestly way more dangerous takes its place. Today we're talking about DIRTYFREE, a technique that doesn't bother hijacking code. It just surgically rips security checks right out of the kernel. All right, so here's our game plan. We're going to start by getting the lay of the land in this post-CFI world. Then, we'll dive into the absolute core of this attack, the arbitrary free primitive. We'll break it down with a simple analogy I'm calling the ghost hole heist, then walk through how to actually build the exploit. After that, we'll see the shocking impact this has on bugs we all thought were harmless. And finally, we'll cover how to fight back.
So, let's set the scene. We are living in a post-control flow integrity world. Think of defenses like kernel CFI, or KCFI, as a super strict bouncer for the kernel's brain. It checks the ID of every single piece of code that's about to run, making sure it's on the guest list. And what this means is that those classic old-school attacks where you just overwrite a function pointer, yeah, they're dead. Done.
And this really frames the new battlefield perfectly. The old way, control flow hijacking, was like messing with the truck's GPS to send it to the wrong address. Defenses now have that GPS locked down. So the new way, data-oriented programming, doesn't even touch the GPS. Instead, it changes the cargo in the back of the truck. Instead of hijacking where the code goes, attackers are now changing the data the code uses.
But here's the catch. Traditional data-oriented programming is, well, it's a huge pain. It's this messy, multi-stage process where you need a perfect storm of vulnerabilities. First, you need a bug to leak an address just to know where to even look. Then, you need another bug that lets you read that memory. And finally, you need a third one that lets you write to it. Finding a single bug that gives you all three of those is like finding a unicorn.
And this is where DIRTYFREE just flips the whole table. It introduces a massive breakthrough that slices right through all that complexity. And it's all built around one single, incredibly powerful idea.
Which brings me to a question. If you had to guess, what do you think is the single most dangerous function in the entire Linux kernel from an attacker's point of view? Something complex, like the process scheduler, or maybe a network driver? The answer is so much simpler it's almost funny. It's kfree. Yep, the humble little function that just cleans up and deallocates memory. The researchers behind DIRTYFREE figured out that if you can control what kfree does, you can control the entire system. And this is the core concept, the arbitrary free primitive. It lets an attacker take a really small, weak bug, like a tiny memory corruption, and use it to trick kfree into deleting any piece of kernel data they want. This is huge because it means you can create a super powerful use after free vulnerability on demand, targeting the exact security object you want to hit at the exact moment you want to hit it. To really wrap our heads around how powerful this is, let's use an analogy. We'll call it the ghost hole heist.
Okay, so picture this. The kernel's memory, the heap, is a high-security parking lot. The really important stuff, like the credential objects that say, I am the root user, they're all parked in this exclusive roped-off VIP section. Now, normally, you can't get your junker car in there, but what if you could trick the valet? The valet is kfree. Using a tiny bug, you slip the valet a fake parking stub that points to one of those VIP cars. The valet, just doing its job, goes and tows that VIP car away. And just like that, you've created a perfect empty spot, a ghost hole, right in the middle of the most secure part of the lot. So what's next? You flood the entrance with your own cars, and the parking allocator, just trying to be efficient, sees that beautiful empty VIP spot and waves your car right in. Game over.
And that right there is the fundamental difference. Traditional DOP is like trying to perform microscopic surgery to change a single letter in a book. It's delicate, it's hard, and it requires a bunch of different tools. DIRTFREE is like just ripping the entire page out and pasting in your own forgery. It's not subtle, it's architecturally simpler, and it's way more effective.
So that's the theory, which is pretty cool. But let's get into the nuts and bolts of how this actually becomes a real-world root exploit.
The attack pipeline pretty much follows our heist analogy to the letter. First, an attacker sprays the heap, filling it with hundreds of their own normal user credential objects. Then, they use a weak bug to corrupt a pointer in a nearby object, making it point to one of their credentials. Step 3, they trigger the kfree call. The valet gets tricked, frees the targeted credential, and boom, our ghost hole is created. And finally, they immediately spray the heap again, but this time with credentials that say UID 0 or root. One of those lands perfectly in that empty slot, and just like that, they've escalated their privileges. So this all sounds pretty devastating in theory, but what does it actually mean in the real world? Well, this is where the story gets really, really interesting.
The research team didn't just play around with theoretical bugs. They took 31 real-world patched Linux kernel vulnerabilities, and they turned a whopping 24 of them into reliable, working root exploits. These weren't cooked up in a lab. These were actual CVs found out in the wild.
But what's really wild is which bugs they popped. They specifically went after vulnerabilities that the security community had written off. Bugs that were assessed as having limited impact, or the kinds of things that get triaged as low-priority garbage. They took that garbage and turned it into a full-blown privilege escalation. It completely shatters this fallacy that a weak bug isn't a dangerous one.
And this wasn't some lucky 1 in a million shot either. The exploit is incredibly reliable. On a quiet system, it worked over 95% of the time. Even on a busy, noisy system, the kind of environment that usually kills heap exploits, it still succeeded almost 90% of the time. That's because they can use clever heap grooming techniques to clean up the memory first. This isn't a theoretical trick. It's a practical, production-ready weapon.
Okay, so that's pretty scary. The obvious next question is, how on earth do we stop an attack this powerful? The good news is, the researchers also gave us the solution.
The defense strategy comes in 2 flavors, and you really only need one. The first idea is isolation. You basically move all the objects that are useful for this kind of attack into their own dedicated, quarantined memory caches. This way, a bug happening somewhere else can't reach over and corrupt them. The second approach is validation. Right before Kfree does its thing, you add a quick check to make sure it's not being tricked into a cross-cache free, which is just a fancy way of saying you stop the valet from towing a car out of the wrong VIP section.
Now, the million-dollar question for any kernel defense is performance impact. And this is the best part. The overhead is basically nothing. The isolation technique adds a tiny 0.28% of overhead. And the validation check? Get this, it actually made the kernel a 0.5% faster, probably due to some nice cache effects. This means there's literally no excuse not to implement these fixes.
Now, let's be clear, dirty-free isn't magic. As the researchers themselves point out, you still need a bug that gives you enough power to corrupt a pointer in the first place. The 7 vulnerabilities they couldn't exploit were simply too limited to even get that first foot in the door. So this technique is incredibly powerful, yes, but it's not all powerful.
And all of this leaves us with one final, really provocative thought. For years, our defenses, our telemetry, our EDRs, they've all been laser-focused on watching the control flow, looking for those classic code hijacking attacks. But dirty-free operates entirely in the data world. So it begs the question, is your security tooling actually watching the data? Is it watching the valet? Or are you still just looking for ghosts in the control flow?